Hello guys, I think we're live now. How's everyone doing? Sorry for the delay. I was once again sorting out all of the live now. How's everyone doing? Oh, this is sorry too for much. The delay. I was there you go. That's better. So I was just sorting out the audio and making sure that we've got everything ready for the stream. So yeah. I think the music noise is, the music volume is okay. Let me know if it's a bit too loud and I can turn it down. Yeah, let me just do some audio checks and then we're ready, we're good to go, right? So as always, pause this. Once again, sorting out audio checks and then we're ready, we're good to go, right? So as always, pause this. Once again, yeah, there you go, I think it's fine. Yeah, welcome to another stream, and today we're going to be doing something you may say a little bit dumb really, but we're going to be learning very old assembly. And why am I doing that? Well, the truth is I never really got to learn assembly properly. The closest I got to learning assembly was when I was at university, I think in maybe second or first year, I can't remember which one it was. We actually did some 6502 assembly, and we learned the very basics of how CPUs kind of work. And it was one of those modules where they teach you a very basic PC architecture and how the CPU loads instructions into memory, reads them, executes them, and then moves on from there. And in that whole module we did learn 6502, but very limitedly though. I can't remember what it was that we were using, but I remember that it was particularly this emulator. I think it was called the Easy65K or something, that had a little graphical interface on it, so you can actually set the pixel colors based on the values in memory. Now I thought, yeah, I could probably get back into that, right? So hence why we're on the stream now. Now there are a few good examples, a few good resources to know here. One of them is probably the most important one, is the 6502.org website, and this has a link to most resources that you may need. And let me turn the music down a little bit, maybe a little bit up for you guys and more down for me. Yeah, so 6502.org contains everything from links to emulators, as well as tutorials to kind of test programs here. So yeah, I mean, I really recommend having a look at this if you are interested in following what we're doing in this live stream. I obviously went for the easy option here, which is to kind of load up a virtual, in fact, a very simple JavaScript 6502 assembler that can actually also emulate the binary that you create, right? And what's interesting about this website, I think it's called masswork.at/6502/assembler. It generates the binaries for you as well, so you can write some 6502 assembly here, and then it will show you the binary, right? And I thought that was quite interesting actually. But yeah, so let's get into it. And the other resource, shall I say, that I'm using here is the Easy6502 GitHub.io, I guess, note here by Skildrick. Is that this guy's name? I don't really know, to be honest, by Nick Morgan. And it's just a tutorial showing you what the instructions are available in 6502 do, and some test programs and so on and so forth. So that's kind of what we're going to be using here, and it does have a little kind of emulator in here too, but I found this emulator here a little bit better by Masswork. Hello Peter, hello dude. Sorry for not reading the chat. I was too involved here in explaining the setup for this video. How's it going, sir? And I hope you're doing amazing. Yeah, it's nearly the end of the week, man. This week kind of went really fast. I don't know how, because I wasn't really that busy at work. I was just doing things that didn't really go towards any sort of production event or anything like that, as opposed to other weeks. But it's still, you know, it went really, really fast. And yeah, I guess it goes faster the more you enjoy it, right? So, but anyway, my guy, good to see you here. Yeah, so let's start, right? So let's do some reading first. So yeah, so in this ebook, I'm gonna show, amazing as always, and yes, this week's went really fast. Yeah, it did. Then why 6502? Why not use for assembly like x86? Well, I don't think learning x86 is useful, and I don't think you'll ever have to write assembly language in your day job. This is purely an academic resource or exercise, something to expand your mind and your own thinking. I disagree with this. I mean, you can definitely write assembly on your day job. Depends on what you do. I mean, if you're a compiler, engineer, or whatnot, and you're working with microprocessors, then you definitely have to write assembly. 6502 was originally written in a different age, at a time when the majority of developers were writing assembly directly, rather than in these new fangled high-level programming languages. So it was designed to be written by humans. More modern assembly languages are meant to be written by computers, by compilers. So let's leave it to them. Plus 6502 is fun. Nobody ever called x86 fun. I do kind of agree with that though. x86 on 64 kind of have a lot of instructions, right? And it's very, very difficult to learn x86 well inside out. Whereas 6502 is a lot simpler. There's way less instructions. I don't know how many. I'll probably say it's like less than 50, right? I'm not entirely sure. So let's, I'm gonna say it's less than 50. 6502 instructions set. And in that way, you can kind of just like memorize what each of these kind of do, right? So you can see here that it's, yeah. So if you look, for example, LDA, you're gonna find it here. And yeah, there's very few instructions. It all fits in one table. So how many do we? Yeah, less than 50. I still stand. My point still stands. So it's much easier to learn than any modern assembly language. So 6502, by the way, is the kind of assembly sort of written for like computers back in the day, like the BBC Micro. That was a popular one, right? I'm pretty sure that the ZX Spectrum also used it. ZX Spectrum. I'm not too sure now. Oh no, Z80, never mind. Yeah, Zilog 80. But yeah, I'm wrong on that one. But yeah, BBC Micro definitely used the A65K based processor, I believe, right? Does it say what it was? I remember reading or watching a documentary about this. Yeah, there you go. So the Mars Technology 6502 processor, CPU there. And, you know, obviously the most popular one is the Nintendo Entertainment System, so the NES. So, you know, it's worth learning these things and seeing how people developed programs back in the day. Hence why I'm learning this. So let's dive in. That thing below is a little JavaScript 6502 assembler and simulator that I adopted for this book. Click assemble, then run to assemble and run the snippet of assembly language. Yeah, so, okay, load LDA. I kind of know what it is already. So this loads into the accumulator and store into the accumulator, I believe. I don't know what SDA is, but, you know, LDA, I know that one. And SDA, I don't know what it is. So we're going to find out. So yeah, I mean, generally with assembly, you have like an instruction and then the operand or operate, or we have the operator and the operand here, right? So that's how it works. And let's see what this does. So if we assemble it and run it, oh, okay. This is what it does. Okay, so SDA, so stores the value that's in the accumulator to this memory address here. Pretty sure that's what it does, right? So let's take a look. So one important thing as well, before we actually take a look at SDA 6502. Actually, maybe we can take a look at that. 6502 instruction set. I was going to take you guys through the architecture of 6502. because we have like registers, we have available memory from the CPU and so on and so forth. But we'll do that in a second. So if you look at SDA, store accumulator address X indexed or indirect. So you can have two different methods, two different ways of calling this particular, let's call it function here, but it's really instruction. So you can pass in, so 81 is the value. So yeah, you can pass in an address and it will store the value that's inside the accumulator to M, right? So store accumulator in memory. There you go. So we can kind of guess what this program is doing already. So it's loading the value 0, 1, which is just 1, I guess, into the accumulator. So you can see here this is going to change. Can we do a debug? Yeah. So if we reset this, can we reset? There you go. Let's reset the registers. You can see what it is now. So the accumulator is 0, 0 here. If we step to the first, so if we run the first instruction, we kind of load 1 into the value 0, 1 into the accumulator. And then the next instruction, STA, we can see what it does. It stores that inside. Ooh, I guess we can't see the, oh, we can see the hex dump here. Right? Oh, not quite. Yeah, I was hoping that we could see the value at this particular memory address here, 0200, because it would be 01. That's why you'd get in that particular byte. And we've run this one. Now we're going to load 5 into the accumulator. You can see here, and then we're going to store the value 5 to this memory address right here, as you can probably tell. And as you can tell, these pixels are moving, right? So I guess these colors are kind of represent the value that we are storing, or the value for the color that we are outputting in this particular emulator here. Carlos Gomez Assembly. Hello, Carlos. It's good to see you, man. Not seeing you in a while. Hope things are going really well, my dude. And yeah, stick around for some amazing content. We're basically just going to be chatting through and reading the tutorial, I guess, right? I did explain kind of like what the setup that I'm using here. It's nothing, too fancy. I'm using web tools, basically. There is a nice sort of emulator here that I'm going to be using for, clarity, which is better than the one in the tutorial. But yeah, so we have stored that number 5 or 05 into this memory address, and now we're going to load 8, which it is here, and then store it on the other memory address here. So okay, so you can kind of see how this works, right? This is basically just putting a value into a memory address, and that memory address is somehow interpreted as the graphics inside this emulator. What made you want to learn assembly? So I don't really know why I'm doing this. I guess it's because I haven't really written that much assembly in the past. I did explain at the start of the video that I did do some of this stuff at uni, and that was probably the only time where I got really close to truly learning assembly. But I do think it's kind of useful to know how things used to work back in the day and how things have evolved right now. So this is obviously 6502 assembly, which is quite old, and I'm talking like NES old. This is the processor used for the NES. So we're not really going to get anything interesting out of this apart from just learning how that CPU architecture worked. However, moving on, once we learn the basics here, we can probably see similar things in more modern languages, or more modern assembly languages like the x86, and then we can start talking about understanding how to code in bare metal, right? But yeah, Carlos, it's useful, dude, and it as this tutorial describes it here, 6502 is actually fun compared to x86, because 6502 has a very little instruction set. You can see it here. There's a website that shows you all the available instructions, and it's like less than 50 basically, so you can kind of learn all of this. But yeah, so that's why I'm learning this particular assembly language. yeah, this is good and well. But if we take the same program and assemble it here, okay, we assemble and then we show an emulator, we can kind of see what the memory layout looks like. So if we single step this, we can see that the PC is at 0000, right? 0000 is basically this binary here. So it's going to read this instruction and read the operand and then increment the PC after it kind of executes that instruction accordingly, right? And you can see, you know, that there are certain changes. There are different addressing modes here. Good luck. Thank you, Carlos. So, for example, you know, if we single step this, AC is now equals to 1. So it has read this instruction here, which says, you know, load into the accumulator, which is the first instruction, as you can see here, the value 0, 1. And the value is after that, right? And it did work right there. And you can see that the PC is now at 0002, which is the third element, right? But this one is an interesting one because this one says store whatever value is in the accumulator to the memory address, to the address 0200, right? And you can see that this is actually more than a byte. Before we were using a single byte to, you know, store the operand of that operation. Now we're actually using 2 bytes. So somehow the program counter is going to be incremented properly now. So somehow the instruction is all of this down here, as you can see. So this is the actual instruction value, and this is the instruction operator or operand here. I believe operand is the value. Is the right name that you give to these things. So if we single step it again, you can see that we're no longer incrementing by 2 now, we're incremented by 3. So the CPU knows that particular instruction takes 2 bytes here. That's all. And yeah, we did that. So we should have stored it somewhere in memory. So if we load, does it say what the memory is? If we do that, show memory, there you go. So we can see here, like we can actually see the memory now. So we have 0200 is 1 and 0201 is now 5, right? Because that's what we did. We essentially just, okay, no, this is not quite right. We haven't got to that bit yet. Let's reset the CPU, right? Yeah, let's clear the memory. Okay. Show memory. Okay, yeah. Never mind. I just had to kind of clear the memory there. But let's run it again, right? So if we run this first instruction, load into the accumulator, single step it, please. Okay, what the hell? Maybe this is a little bit buggy. Let's do it again. You lost me at assembly. All these numbers look confusing. And that's the beauty, Carlos. Each one of these numbers here, they have a meaning in the CPU, right? So assembly is basically, if you think about it as a very, 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 very simple programming language, that's what it is. It just has like an instruction and a value that you pass into that instruction. That's what your programs compile to, right? But even assembly isn't what the computer, understands. What the computer understands is kind of this here. This is the compiled assembly. So this is basically a one-to-one mapping. So each assembly instruction is basically a one-to-one mapping in these numbers here. So like you get, for this one, this particular operation here, LDA translates to A9. That's what it is. And you can see it here in the instruction set anyway. So if I look at LDA, which is A1, not quite the one we want. We want A9, so this one here. So load the immediate address, right? That's the instruction. It tells you what it is. That's basically what the assembler does. It just compiles each of these instructions to something like this. And, I was explaining that the other one here, the next instruction, STA, which stores whatever values in the accumulator to the memory address given here, that translates to 3 bytes. So the first byte is always the operator, and the second or or also the third byte are the operands, the values you're passing into that instruction. And that's exactly, that's it. It's just as simple as that. Obviously, we can do much more complicated things with assembly. and that's why you can compile languages down to assembly. But you know, in a nutshell, this is how your computer works and how it reads instructions from your programming languages. So yeah, and if you stick on, you might learn something, dude. But yeah, I mean, looking back at this, let's show in the emulator here again, because I think we bugged it out last time. Show in emulator, assemble, show in emulator. Okay, yeah, we've definitely bugged it out because it's not really showing me the emulator. So let's assemble it. Okay, show in the emulator. Fine. Now let's load the memory. So the start memory is there. Oh, live update, yeah. Oh, show memory. Display as ASCII characters. Yep, that's fine. So let's clear the memory. Okay. Now if you single step it, oh, BRK at 00. I don't understand what this is. Maybe we shouldn't have cleared the the stuff on the memory. Maybe we're not supposed to do that. I just want to have a walkthrough on the memory itself. Yeah, let's change these instructions a little bit then, right? So in this case, let's put 1. Yeah. Let's start at 0, 1, 0, 0. Okay. I mean, it still didn't work because it didn't update the emulator stuff, right? Let's assemble it. Okay, show an emulator. Now it worked because I can see it here. I just watched a video on modules. Was once working on a C++ legacy code base that took 3 minutes to compile. I mean, that's pretty good, dude. 3 minutes is nothing. And thank you for joining the stream, 921, and thank you for watching the video, dude. You know, feel free to comment if you've got any requests or any questions. Happy to help. But yeah, 3 minutes to build, dude, is nothing. Trust me. I've seen a lot worse. I've seen hours for builds, believe it or not. Granted, not only C++, but the whole kind of like OS, but yeah. 3 minutes is just a sweet spot, isn't it? Yeah, let's see if we can load the memory now. So show memory. There you go, 000, and let's do a live update on the memory. So let's single step it. So the first instruction that we had, as you can see here, was load into the accumulator 01. And then we're going to go to the second instruction, which is this one here, and we're going to store whatever is in the accumulator to the memory address 0100, right? So if you single step that, we can see that we've stored the value at 0100, as you can see here. So this is kind of like a RAM. This is the RAM basically of your 6502. And now the next instruction is to load into the accumulator the immediate value 5, right? So we're going to single step it, and here we have the same thing again. So we just replaced the value 01 to 05 on the AC, and we're going to store it into 0101. So this one is going to be 05, right? This is all we're doing right now. And then the same thing with a value 0A, and that is it, right? This is basically it. It doesn't take too much to understand what's going on here. I'm going to skip some of this because it's just going to explain what we already know. Now, registers and flags. We've already had a look at the processor status section, so the bit with A, PC, etc. But what does it all mean? The first line shows the A, X, and Y registers. A is often called the accumulator. Each register holds a single byte. Most operations work on the content of these registers. SP is the stack pointer. This stack pointer is very important, by the way. This is probably how we create stacks, right? We can create call stacks and all sorts of stacks with this. We're not going to look too much into that, I believe, anytime soon. There you go. I won't get into the stack here. But basically, this register is decremented every time a byte is pushed onto the stack, and incremented when a byte is popped off the stack. So it's basically just a computer science stack, you know, a stack of bytes. PC is the program counter. It's how the processor knows what point in the program it currently is. So we've already have seen some of this already. So every time we do a single step here, if you reset the CPU and clear the memory here, can we clear the memory? Clear memory. Right. If we do that, oh no, I didn't mean to clean the whole memory though. And this is what's annoying about this. Can we single step it now? Yeah, anyway, so you've seen it that whenever we type in single step, it knows exactly at what byte our program is at, right? So that's what the program counter does. It just keeps track of where the program is. And obviously you can change that program counter, you can do jumps and whatnot. That's how kind of like loops are implemented and branching. So we're going to take a look at that in the future as well, I guess. So in the JavaScript simulator, the code is assembled at starting memory location 0600. So in the JavaScript simulator, the code is assembled starting a memory location 0600. So PC always starts there. Okay, so PC always starts at that particular location. Okay, instructions. Instructions in assembly language are like small set of predefined functions. All instructions take 0 or 1 arguments. Here's some annotated source code to introduce a few different instructions. So yeah, we kind of know what some of these are already. LDA. Oh no, we don't know what TAX is. Transfer the value in the A register to X. Okay, so transfer A to X, increment X, I believe, right? Yeah. So increment the value. We increment whatever's on the X register. ADC, add the hex value 04, or C4 in this case, to the A register. Cool. MBRK, break, we're done here. Okay. So yeah, I mean, we can take a look at each of these individual ones anyway. So TAX, for example. So TAX, these are the values. So transfer accumulator to X. So there are, I guess, it takes nothing, right? Inks, so increment X also takes nothing here. So you can see it here. And is this for any reason? Okay, I thought it was a Zelda song, but I don't want to get a copyright strike, guys. Are you guys following, by the way? Like, are you actually interested in the shit, or am I just doing something extremely boring here? Please let me know. I can switch topics quite quicker if it is too boring. And ADC, add the hex value C4 to the register A. So let's see what ADC actually does and how many how many different calling methods we have here. Yeah, I mean, we haven't spoken about this yet, but every instruction in 6502 either has like an immediate mode or an address mode, so you can pass in like a literal value, so like 05 to be stored in the accumulator, or you can pass in a memory address, which is going to store the value in the memory address from 05 into, you know, you can have indirection here. So it's like pointers in programming languages. So ADC 69. Can we have a jump here as well? Okay, we can have jump. So jump to a new location, PC +1. Okay. Yeah, there you go. So what I meant is you can have absolute addressing or indirect addressing, right? So we do have increment. Can we decrement? Dex. There you go, decrement X, right? Because what I'm going to try and do here is, like, we had this first example where we just fill in the pixels, right? So I'm wondering what happens when we just do a for loop here. So I'm going to try and implement a for loop. And a for loop is usually done by jumping things. So if we look at jump, I don't know why it gives me like the 5th occurrence instead of the first one. So jump absolute value, right? So let's see what this does. Jumps to a new location. Let's see if we can implement a jump here. And for this reason, we're going to have to use the graphical tutorial here. So in the first one here, we're going to load 1 into the and 3 cycles. So it definitely want the absolute one. Anyway, yeah, let's see that. So we're gonna load 50 into the accumulator. We're gonna decrease that number every time for like one iteration. And whatever number we have currently loaded into X, we're gonna store it into I guess the accumulator, right? And then we can pass into transfer XA, TXA. Is that a thing? So TXA, yeah, it seems to be a thing. So transfer from X to A, right? But it probably doesn't zero out the buffers, and that's kind of what we want, right? So transfer X to A here. Let's see if that works. So if we assemble this and we do the debugger, I'm going to zoom in a little bit so you guys can see it better. So we step it, we have 32 there, and we have 32 here as well, right? And then we can store whatever is in the accumulator. It's STX, I think, yeah. So start index X in memory. What's the difference between STA and XTX? Is there any difference? Store accumulator in memory. So why is STX different? Oh no, we do have STX here. Store index X in memory. Okay, X goes to M. That's all. I mean, maybe we can use that straight away, right? We don't need 2 instructions, so we can simply do an STX in here. So let's assemble that, debug it. Okay, so 50 is that color there, apparently. So, and now what we're gonna do is let's build 33, and I'll tell you why. So we're gonna decrement whatever's in X. So let's see if that works. So debug it. Okay, and then we store that. Okay, cool. And then in here we're gonna do a jump. And we're gonna jump to, I guess this has to be an immediate mode kind of thing, right? So we have to pass in the bytes. So yeah, this is interesting. So we have 2 bytes here, 1 byte here. So I'm on 2 now. So this is 0, 1, 2, 3, 4, 5. So I want to jump again to 0, 1, 2. So it's 0, 1, 2. Yeah, I want to jump into the third thing, right? So maybe if I do this, does that work? Does it work like that? I don't know. Let's see. Syntax error, jump 0, 3. That does not work, right? Maybe we can find out. We can get a little bit ahead of ourselves. So jump 65 or 2. Example. For example, if address 0300 contains that. Ah, okay. I've realized why it didn't work, by the way. Nothing to do with that, what we just read. But it's something to do with how this PC thing works, right? So if we remove the jump here for now, let's just remove it for now. We assemble it and we debug it. So the first instruction is at 0602, right? So that's where we are here. And then the second instruction is going to be right there. That's the second instruction. That's what it is now. So that's where we want to jump, basically. So if we do that, and then if we do decrement x, and we store into there, and we jump to here, this is kind of what we want, right? So I'm going to assemble it, and then it did work now. If we step in, and obviously we want to keep track of the, we want to keep track of the memory address we want to kind of store things in, right? Because currently we just have an infinite loop that changes the pixel value every time. You see? So it's moving like this here is moving every time. See? And that's what we're doing. It's just an infinite program that jumps on itself. And yeah, that's fine. But I want to move on the pixel as well. Now, what's the best way to do that? I guess we can use another registry for this particular case here. I don't know. Yeah, we literally can't do pluses there, right? I guess. Maybe you know, we've got something cool now. Let's keep running and then see what happens. We can go back to this program up here. So instructions, we've read this through. We know what break does. Assemble the code and turn on the debug and step through the code, watching the A and X registries. Yeah, we get the gist, right? You can change the value of the registries with instructions. Fair enough. In the simulator below, type don't paste the following code. So let's see if we can do that. LDA, and we've got the immediate value 80, and then we store that into memory address 01. Okay, so we stored that into whatever is pointed at as 01. That's interesting. And we add to C. What's add C again? ADC. What's ADC? So add with carry. Okay, so add with carry. So it sets the carry bit. All right. Yeah. So for arithmetic as well, guys, if you've not done this before, there are functions like add C or add with carry. And this will add two numbers, but then if they overflow, it sets the carry flag. And as you can probably guess, there are a few flags here. So you can see all these flags there. So the carry flag is the very last one here. And you can kind of set it basically yourself in this emulator, but you know, if your add C adds two big numbers that overflow a byte, for example, then this carry bit will be set. We can figure out how we can do something like a multiplier, like multiply two numbers later, right? That would be an interesting exercise as well. And then we add C 0 1. Now this is interesting because this is an indirection right here. So let's assemble it and let's debug and see what happens. So we load into the accumulator 80, and then with STA 0 1 we store whatever is in the accumulator 0 1. Okay, so we're kind of gonna double this, and then we add whatever is in that memory address back to the accumulator with a carry, right? So we add 80 to A0, which gives us 0 there, and we set the carry bit there. Okay, so let's do this again so you can see what happens. So we're gonna step through, we load A0, right? Which is good. So if we do another, and then we're going to store this value into that memory address 0 1. So, 0 1 now holds A0. We can't see this here because it doesn't, it's very bad design, this emulator. They should show you the hex dump at least. Yeah, no, it only shows us what we have on the program itself. But then we're going to load whatever we've just stored in 0 1 to be added to the accumulator. So we're going to add A to A. That's what this does, right? And what happens when you add A to A in hexadecimal? You get 16. And what is 16? 16 is one more than the maximum value, which is 0 0, right? And plus the carry flag. So what we expect here is that this last flag here, once we step through, it's going to be set to 1, and then the value of A is going to be 0 0. It's going to wrap around, right? And this is exactly what happened, right? No surprises there. But you consider that another value another flag went up, which is the N flag. I can't remember what the N flag is for, but yeah. Is it non-zero flag? What was the N flag? So what we have is a 6502 N flag. Status flags. So N is the negative. So if anything results in a negative, then this flag is going to be set. That's interesting. So V is also set, right? Because there's an overflow flag, and we can check that. Where are we? So V is not set there. Let's reset this. Okay, so we load that in. Okay, yeah. So V is the negative, and it's set to, sorry, it's the overflow flag, and it sets to 1. Because this operation did overflow, right? I guess. Cool. Anyway. An important thing to notice here is that distinction between ADC01 and ADC01. Yeah, the first one is the literal value 01 to the A register, but the second adds the value stored at memory location 01 to the A register. We talked about this earlier. Assemble, check the monitor checkbox, then check the monitor. Okay. Okay, cool. So we do have a... this makes things much easier. Much easier. I didn't realize that we had a memory thing. But yeah, if we run that again, you can kind of see what we do here. So step through. So let's reset this, step through it. So we've got loading. We start into 01 here, the value 80, and then we load that value in and then add it to the accumulator. Good. Branching, which is the next important thing here. So far, we've only been able to write basic programs without any branching logic. So let's change that. 6502 assembly language has a bunch of branching instructions, all of which branch based on whether certain flags are set or not. In this example, we'll be looking at B and E, branch on not equals. Okay, so let's see what this kind of does. See if we can debug it before even running the code. So LDX is going to load into the X register the value 0A, and then we set a label here. So I guess this is for jumping on later on, right? So we can kind of branch not equals there. Anyway, so we create a label there which we can jump to later on. So we decrement whatever is in X. So we're going to have 07 in X now. We store whatever is in X to the memory address 0200, And then we're gonna compare to the value 0, 3. Okay. And then we decrement here. We're going to compare the X register to the value 0, 0, 3. And if it's not equals, we're going to jump to decrement, right? So, okay, we have a better way of doing this now, I think. So right up here, right? This is where we were at with the program before. So we had something similar. We had LDX 003. Now we know that we need to kind of hold our index into a variable somewhere, right? And we can put the assemble here. But yeah, I mean, let's do something similar. So we got decrement, which is there, and we decrement X, and then we're gonna basically store. Actually, yeah, we're gonna store whatever's in X before we decrement. We can do that here. So we do 50 first, and then we can compare it, right? So compare X. I think that was the thing, to the value 0, right? So whenever it reaches 0, we're going to branch on not equals to decrement, right? So we're going to jump onto this until we reach 0, which is cool. But we still need to have another indirection here. We still need to hold into Y, I guess. Let's do that. So we're gonna LDX or LDY the value 0, 2, 0, 0, and this is gonna keep track of our index, right? So we're gonna store whatever is in Y to where? So 0, 2, no. 0, 1, 0, 0. That sounds fine to me. 0, 1, 0, 0. I'm gonna put that after we decrement, actually. So this is gonna be whatever's pointed at this address. Can I do something like I want to get whatever value is here? So value of, let's see that. So 6502 assembly, value of memory address, right? How can we get that? I'm sure it's something like you have to put parentheses on it or something. There you go. So whatever value is on 1000. Okay, good. So yeah, let's do that. I'm pretty sure that's the way to do it. So if we do it this way, let me think this through. This is obviously a much more complicated program than it needs to be, but we can write something cool already. So store into Y whatever value is in here. And we can load into Y that first value. I'm going to store into Y whatever is Y is going to be stored here, and then we want to decrement Y. Is that correct? Yeah, we want to decrement store it, but then we also want to load it. We want to load it every time, right? Or do we? I'm a bit confused now, to be honest with you. We're using two registers, probably don't need to start to read two registers, but we can probably do with one register. But we store into X. Ah, okay, yeah. So this is the key. Whatever's in this memory address, whatever the value of this memory address is, we're going to put it into X. And we decrement the X. Oh no, this is not right. This is not right. Store into X. Oh no, that was right, yeah. That was right. This value is simply our little I variable, basically, that's tracking the position. If you think about C++, if you're doing a for loop, this is our I variable, this here. And we decrement X. What do I do with X afterwards? You compare with X. Okay, yeah. Yeah, we do need to put whatever is in Y in here, to be honest, before we read it in. And then we decrement X down here, decrement Y. Yeah, we just do the storing here. And we compare. Yeah, I think this is okay. Let's see. Is it gonna assemble? I mean, it does assemble at least. So, what does it? No. LDY line 2. So LDY doesn't exist. Great. Does LDY not exist? Have I written something wrong here? Ah, yeah, this is an 8-bit register. Ooh, okay. Can I do maths here? So can I add this plus whatever? Does that work? The 6502 is a little endian machine, so any 16-bit 2-byte value is stored within the LSB first. So the least significant bit will be stored. Byte will be stored first. We know that. So 0 page is an addressing mode that is only capable of addressing the first 256 bytes on the CPU memory. You can think of it as an absolute addressing for the first 256 bytes. Yeah, so we only have a byte's worth of information to hold addresses. The instruction LDA 35 will put the value stored in memory location 35 into A. The advantage of 0 page are 2. The instruction takes one less byte to specify and it executes in less CPU cycles. Most programs are written to store the most frequently used variables in the first 256 memory locations, so they can take advantage of 0 page. Right. So indirect. The jump instruction is the only instruction that uses this addressing mode. It's a 3-byte instruction. The second and the third bytes are absolute addresses. Okay, maybe it isn't what we wanted to do. So indexed, indirect. There you go. This mode is only used with the X register. Consider a situation where the instruction LDA 20X, X contains 04, and the memory 24 contains 0024. The first X is added to 20 to get 24. The target address will be fetched from... Okay. Right, I think we have to use X then? Is that correct? If the instruction LDA is 06 and X is 60, then the target address will be 20 T0 plus 60. 120, but the carry is discarded in the calculation and the target address is okay. So we can do commas here, right? We can kind of do commas to do this memory address plus that. Right? Let's try that again. Let's see if this applies here. So we store into X whatever is in this value. Now I don't think we can do this though. LDY 0200. So this is becoming very complicated very quickly. What do I want to do? What's the goal here? The goal is to load into the accumulator, shall we say, every value for the colors, right? So maybe we can use the accumulator here. So LDA 32. So we replace this with, is decrement A a thing? Decrement DEA. Decrement A is not a thing, so we can't do that. It has to be X. We do need the X here. Is decrement A not really a thing? Yeah, so we've only got 3, so decrement. Decrement index X by 1. Decrement memory by 1. Okay, so it decrements the memory address. We can do that. Which is better, right? Because we can just store, I guess, without having to do I here. I'm thinking very hard. Thinking very hard here. So we can do indexes. So 0, 2. Absolute index addressing. Okay. Potentially this is what we're gonna have to use, something like this. I'm getting lost in the tabs. So we load into the accumulator 32, which is 50. Now, do we want to load into Y? Probably not. I mean, we can load into X, right, I guess. So load into X. This will be our index, right, into... We're going to load 0, 0 into X. That's fine. Now, what we want to do is... Maybe it does have to be X and this one has to be Y. Because we can decrement X and we can't decrement... From the looks of it, we can't decrement the accumulator registry. So... Oh, Peter, you're saying something, but I can't really see what you're trying to say, dude, because this heart thing is really annoying, man. Where is the thing where it says, you know, look at the HTML thing? Oh, inspect, there you go. There you go, can we remove that? Dot. Fair enough. Nice message. Yeah, this is getting very complicated. I'm gonna change the Zelda song because we always get a copyright strike. Yeah, we're gonna store into Y. So store into Y whatever is in Y to 0, 1, 0, 0. So, okay. Can we increment now a particular memory? Oh no, yeah, we can load into Y, right? That's fine. So we load into LDY whatever is in this memory address here. And we're going to increment increment y. Is it that? In x, in y. Okay, increment y. So increment y there. And we're going to store whatever is in x into memory address that plus y. Does it work here? Yeah, it does work. So store whatever is in there into the value that's coming from this memory address here. Wait, even better, can we do this? Does that work? We'll see, we'll figure out. And at this instance, we decrement x, so the pixel value goes down, and we decrement or increment y, which is already done, I guess. And we do it after this. And we compare x to 0, 0, and we decrement it. Assemble it. Does it work? No, it doesn't. So we cannot have this here. So how can we index this? Oh wait, this is even simpler. Like, I don't need to hold things in whatever it is. It should just be this. It should just be that, right? So assemble it, and that still doesn't work. Great. Absolute index addressing, okay. Syntax error line 6, this one here. So store whatever is in X into that memory address. Maybe store doesn't take that, actually. Store doesn't take the, whatever this is called here. Immediate address, indexed indirect, right? Is that correct? Well, not even that, we just want 0 page, or indexed indirect, indexed. Indexed, that's the one. Absolute indexing address, so store into A. Yeah, I can see that SDA takes that, but I'm not sure if store into X. Let's see. Yeah, it doesn't take that, right? Absolute value, 0 page Y, 0 page indexed. It seems to, right? I mean, what's the difference between SDA here? So we have these ones here, indexed. X indexed, indirect. But STX does not have that, right? Yeah, we've got 0 page, so it doesn't support that. Okay, another problem. So what can we do here? Can we transfer over whatever is in A to X, and then we do transfer A. Okay, that worked. That kind of worked. So let's try this now. This is an infinite loop again. Let's stop that. Let's kind of see if we can debug it, at least. So we decrement X, right? That's the important thing. So we run the monitor here, and we start at 0, 2, 0, 0. Hello, King Hader. How's it going, dude? That's a name I haven't heard in a long time. Good to see you on stream, man. So let's reset everything and let's debug it. So we load 32 into X, which is this function, this instruction here. Then we load 00 into Y, and we store whatever is in Y. I mean, this is not necessary into this memory address. We don't need it anymore. And then we decrement here. So at this stage, we're in here, right? So we kind of transfer whatever's in X to A. Or maybe not. Like, I don't know what's happening now. So what the hell is happening here? Let's remove that. I don't think this is needed anymore. Star into Y 001. Increment Y, yeah. I mean, let's assemble this again. Reset it all. And then load 50 into X, which is what we did here. And then we load 00 into Y. And then it zeros everything. So we're at, I don't understand what's going on now. 1, 2, 3, 4. 0, 1, 2, 3. 4, 5. Transfer whatever is in A to X. Ah, okay, so it'd be X to A. That's my bad. Oh, good things, yeah. Last week I was traveling nice, dude. Yeah, I mean, last week I wasn't traveling last week. It was the week before that, actually. But yeah, where did you go, dude? Anywhere nice in the world? Now we transfer it to A and we store whatever is in A. Ah, okay. And we increment Y in this case. We increment Y. We decrement X. We compare X to 0, 0. Not true, so we're going to go to decrement again. So we transfer whatever is in X to A now, right? Ah, okay, so that takes a few instructions, the decrement, the comparison, and the decrement here. And then we store that. Okay, now it kind of works, I guess, right? So you can see, like, we're setting the pixels, and that's what we wanted to do. Great. I mean, let's see if we can kind of just run this. There you go. Now, if I wanted to do more pixels, I don't know how many more pixels I can do. So maybe, oh, 50 did up to there, I guess. I don't know. So let's do 100. Let's try that one. Or more than 100, I guess. And good. So we can kind of set some pixel colors now, right? Which is interesting. Now, how would I do the full screen? I guess, you know, just one of them is kind of 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. That's 16. Oh, so there's 32 pixels by, I guess, 32 pixels, right? So we clearly need how many of these to fill up the entire screen? So 32 times 32 is 1024. So we need 1024 iterations here of this kind of thing. So how do we do that? Because, you know, we can only store a byte here. So basically we have to run the byte, which is up to 16, right? So FF, what's FF? 256. I'm pretty sure it is, right? And again, the calculator does help us in this case. So 256. You can see that. Yeah, sorry, 255 would be FF. So we can do this how many times? So 1024 divided by 256 we need to do this thing 4 times, right? So we basically need to check the carry, I guess, 4 times. Right, this is interesting, because now I'm gonna check the carry 4 times here to make sure it overflows 4 times, and I need to yet another registry, right? So this is maybe where we can store things into the RAM. Yeah, I really hit the matrix and the algebra. That's what I like to hear, man. So now I'm gonna check the carry to make sure that we overflow 4 times, right? I don't know how I'm gonna do that, to be honest. I mean, we must need another little branch equals here, right? So let's see what branching we've got. Branch not equals. Let's see branch. Let's search for branch. What do we get here? Where are all the conditions? There you go. So conditional branching instructions. So branch targets are relative signed 8-bit address offsets. An offset of 0 corresponds to the immediate following address, or blah blah blah. So branch on carry set. Okay, so we can do this, I guess, right? So branch on carry set. What is this gonna do? So branch on Z equals 1 on result 0. Yeah, we can do this, right? I guess we compare. Branch on carry clear. Now these are interesting ones. He's branching in here. I'm thinking of something like, you know, so quarter, and having something like, you know, we load into the accumulator whatever is going to be in our let's say 0, 1, 0, 0, right? So we load into whatever is here. So let's do load into the accumulator. We're gonna zero out the buffer in this case. So 0, 0, and we're gonna store into whatever is in the accumulator to this is the interesting thing, 0, 1, 0, 0, right? We're just gonna need that. So whenever we hit a quarter, we're going to load into the accumulator whatever's value in here, and we're going to add to the accumulator. I guess that's what we want, right? So where's my instructions there? So ADC, that's the one we want. I had no idea why it doesn't give me the first like instance of the find. So ADC, we want the absolute value. So add memory to accumulator with carry, because we want to set the carry here if we need. Well, yeah, we don't really care about the carry, but I guess we can have an absolute there, right? So ADC, and then we have the operator. Okay, and it tells you how many cycles it needs. So immediate mode is always the best from the looks of it. It takes 4 cycles, and yeah, we can do. Right, so quarter, add 0, 1 in this case, right? That's what we want to do. So increment it every time. So once it reaches 0, compare x to 0, 0, and branch on not equals decrement. Can we do 2 branches on one comparison? Is that a thing? So branch is set to 1. Is that what that means? I do wonder. So can we do branch on carry set? It's BCS, right? We're going to jump to quarter. Maybe not. Maybe we can do 2 comparisons here. Maybe at this stage we can do... I mean, this is definitely our first for loop that we want. We want to do a for loop, you know, whenever we are decrementing the x here, right? To keep the value of the pixel. So we're just going to keep wrapping around. But every time we set a carry, we want to go back to the quarter here. That's what we want to do. Huh. No, I guess it's not even the carry that I want. I want to know which flag will overflow this. Oh gosh, this is difficult. Branch on carry clear, branch on carry set. Branch on result 0. So where's the 0 register? 0 page, 0. We're gonna have to Google again. One 6502. Let's look at the registers. Okay, the flags, processor status. The 0 flag. The 0 flag is set if the result of the last operation was 0. So if the last operation was 0, does that mean whenever I decrement, that will be a 0? So whenever I decrement this, and does my then branch on thing, branch on carry clear, branch on carry, branch on 0 result. Branch on overflow set. Yeah, what I'm looking for is like branch on a 0 value and also clear the flag here. That's what I'm doing. Because if you look at the clear options that we have, for example, overflow clear, branch on V0, so you can clear the decimal, clear Z. Can we clear the 0 flag as well? Compare. No, it doesn't look like we can. Oh, this is getting difficult. This is really getting difficult. Addressing relative, assembler, yeah, new operation. Branch on the 0 flag equals true. Do I understand what the 0 flag is? The 0 flag is set if the result of the last operation was 0. So at this stage, I am wondering if I can just do something like, you know, branch on, what was it called again? Oh gosh, I keep losing it. So branch on result 0. So BEQ. Wait, is it just BEQ? BEQ on result 0. Can I do a BEQ here to quarter in this case? Does that work? Does assemble work? Because I'm not comparing here. I do wonder if I have to do a comparison. So comparisons. Compare with the accumulator. Okay, so where are we actually storing the value? So tax into, store into the accumulator. So whatever is in X is what we... I guess I need to compare it with 0, 0 here, right? What is branch equals? Branch not equals. I guess it's the same. So comparison is 0, 0. Oh. Yeah, so in this case, because we're loading whatever we have from X into A, right? So X is what keeps decrementing the kind of the value for us here on for the pixel color, right? That means that whenever we reach 0, so we've done 256 different pixels, then we go into quarter, and as we know, we have 1,024 pixels overall, which is a quarter, which is 4 times 256. So this should work, right? I do wonder. So let's assemble it. Let's see. Oh, there is syntax error, LDA, whatever, LDA. There's a syntax error there. So load into the accumulator whatever is in here. Okay, yeah. However, this does stop eventually. Now, why does this stop? Because my quarter isn't actually loading into X again, the initial value of FF. That's what we need here. We're gonna keep going with the index, right? So I guess whatever LDY is, we're gonna keep going. Oh yeah, this is what we need to do here. So, oof, this is getting difficult. So if instead of, yeah, because now we also need to increment this here by FF, you see. This is getting more difficult the more I think about it. So this initial offset is going to have to be it's going to have to be kind of shifted down. So instead of starting here, we're going to start here and then increment the same amount. Now, it would be nice if this kind of did something like this. Does this work? No, yeah, this does not work. So immediate address, I guess, is your page. That kind of sucks, doesn't it? Let's see what store into A does. Store from the accumulator. What modes can we have? Yeah, I mean, we can have X indexed and indirect, so we can only do an X index here. Indirect and X indexed. So we're using this mode right now, which is the absolute one plus whatever is in Y, this one, sorry. What we want is something like this. So indirect. So let's see what this does. Oh, it doesn't give me an example. This is great. But this is kind of what we want, right? So click for details. I don't have a detail. What we want to do, I guess it would be something like this. Oh. Like in the quarter, we definitely want to zero out y, which is the variable that's kind of, or the registry that's keeping the iteration for us, right? So we do want to do something like LDY. I guess, you know, really what we want to do is like put this at the start, like right here. Now we want to set, you know, all these things back to what they were at the start of the program. And then we can use the memory to store the actual offset into the screen where we want to set things, right? Oh gosh, this is getting difficult. So we load into the value 0, 0. And we store that in there. Huh. See, but I kind of want to store like an address now, which is 2 bytes. So how do I do that? Oh gosh. Store 2 byte, read 2 bytes, 6502. Dude, this is getting difficult. Guys, I'm gonna drop it here, but I think we're gonna definitely continue this though. I'm gonna 100% save this because I am interested myself, and when I do fix this, I'm gonna probably continue the stream on. But so far we did learn quite a few things. We learned some of the basic instruction set in the 6502 assembly language. We did learn some branching, I guess, and some of the flags, right? So it's been useful regardless. Thank you all for watching. I'm not sure if it was interesting to you guys, but you know, if you can like the video, I appreciate it. And stay tuned, because this week I'm gonna try and record a long form video, an actual video on YouTube, not a live, where I talk about, I guess, C++ Const Expert and how I approach it. So yeah, I'm writing the script right now, so hopefully it's gonna be done this week. If not, it'll definitely be done by next weekend. But yeah, thank you all for watching, and I guess I'll see you guys in a bit. Bye bye. Lord Hog, good luck in the debugging. Thank you, Lord Hog. I will definitely debug this tomorrow. I just don't have the mind for it today. But it's been useful anyway. We've been able to set quarter of the screen in different colors, right? Now I just got to figure out how to do an extra level of indirection where we store addresses in the memory itself, and then read 2 bytes into registries and then use that as an offset, which is kind of turning out to be difficult, but I'm sure it's not as difficult as I'm making it out to be. But anyway, thank you guys, and bye bye.